Welcome to Spring LIB.
Hello everyone, today we're doing chapter 18, problem 36, and this problem asks us to draw the product formed when phenol, which is a benzene with an alcohol, is reacted with each of these reagents. So there is quite a bit of reagent, so just bear with me while we work through this, but if you understand why you form the products in each one of these reagents, you guys will be in very good shape for any upcoming quizzes or assessments. So let's start with A. And before we start with A, so I'll just draw A here. Before we start with A, let's identify, so a phenol group, we know that we have an oxygen, and we know oxygen has lone pair electrons, so we need to first identify where the substituent that we're going to add is going to be placed on our benzene ring. So we know that because oxygen has lone pair electrons, it can go through some resonance structures that places a full carbanion, a full negative charge on the benzene ring. Therefore, it's going to increase the electron density on the benzene ring. Therefore, it is an electron donating group. Therefore, we know the electron donating groups direct, ortho, and para on our benzene ring. So every one of these reagents, we're going to have two isomers, or most of these products will have two isomers, one being the ortho isomer, one being the para isomer. So for A, we see that we're reacting this phenol with a nitric oxide and sulfuric acid. So we know that we're adding a nitro group to this. So fortunately, this problem does not ask us for the mechanism, because then we'd be here forever doing these mechanisms. But hopefully later in the textbook, there will be some mechanistic questions that we can go through to fully confirm why we get an NO2 group when we have these reagents in these type of problems. So one is going to be an NO2 and nitro group on the ortho position, plus we'll get the para isomer having that NO2 group at the para position. Now for B, we're adding SO3 with sulfuric acid. So we're adding the sulfonol group here. So in B, we're once again adding the sulfonol group, but now SO3H, but now we're adding it in the ortho and para position, just like this nitro group. So all of these reagents are in your textbook, so you can just refer to that to confirm the mechanism of these type of problems, or look at the later problems that we'll cover in this textbook. But it's also good. Organic chemistry does not have much memorization, but for simple things like these are not too hard to memorize. And once you understand the mechanism, it really helps you to clarify why a certain product will be formed. And then that really takes the memorization completely out of it, is because you can just rationally work through the mechanism and obtain the product. So before you guys are doing that, or just for some time saving, or just for some multiple layers of verification, memorizing the products for these reactions are helpful. So now let's move to C. C, we have now this alkyl halide group with Lewis acid. So we know that this is going to be Friedel-Crafts alkylation. So we're going to add 2 carbons onto the ortho or onto the para position. 2 isomers being formed, one the ortho and one the para isomer. Once again. So the ortho is going to have 2 carbon, and then the para is going to have, once again, 2 carbon. So in D, let's see what we have. Now here we have Friedel-Crafts acylation now. So in D, I'll draw the acyl group just so we can clarify. So we have 1, 2. So we have 1, 2. And then we have diethyl, like this. So we're adding this group onto the ortho and onto the para position in separate isomers. So this is D. plus its isomer, para isomer, being this one. So now let's move on to E. E, we now have halogenation, but we have halogenation with some sort of Lewis acid. So I'll do E now in different color just to help us clarify over here. So E, we're adding bromine group, but now because we have this acid, we reform this Lewis acid through every cycle of adding a bromine onto this molecule. So now a consequence of that is that you will get polybromination. So you will get bromination at all your available directing sites. So you will get bromination at both ortho and para site because you're reforming this Lewis acid and you're making this bromine group, the diatomic bromine, into such a stronger electrophile, because in essence what you're forming is Br plus bound to FeBr3 minus. So you're now making this bromine group into such a stronger electrophile now. So because you're adding it in such a stronger electrophile, you're making such a stronger electrophile, and you're reforming this Lewis acid every time, you get a consequence of having this polybromination occurring. So what you're going to end up with is one product with every single directed site, so both ortho and the one para, having bromination occurring. Now F, that problem is resolved because now we don't have that Lewis acid. So once again, we're going to have only one bromine being added to either one of the ortho positions or the para position. So once again, because we have no Lewis acid in this time, we will get that substitution product with having one isomer at the ortho position and one isomer at the para position. Now G, we're doing the exact same thing as an E, but we're just changing the identity of the halide. So instead of Br2, we have Cl2, and instead of FeBr3, we have FeCl3. So G is exactly like E, but now instead of bromine, it's going to be chlorine. And this is just because we're just changing the identity of halides. Now in H. So in H, what we're doing is we're taking the product of A, and then we're adding a reducing agent here. So what we got to do is, so let's draw the product of A. So we have two products for A. So we'll draw the products of A first. So this is H. And this is one isomer. Then we have the other isomer. And now we're adding tin and a strong acid. So we know that tin with a strong acid, using your textbook as a reference, is a reducing agent. So because it's a reducing agent, we know that the only reducible groups here, alcohol is already at this most reduced form. If it was an aldehyde, we could reduce that, or a carboxylic acid, we could reduce that, but alcohol is already fully reduced. The aromatic ring here is too stable to be touched. So the only thing that's left is the nitro group. So we can reduce nitro to amine. So we can reduce the ortho and para isomers into ortho-para isomers of amine. So NH2 with tin and a strong acid or any sort of reducing agent, NH2. And now let's switch colors again. So let's do I now. So I, we're taking the product of D, then adding another reducing agent here. So we're adding the product of D, which is the Fiedel-Crafts acylation product now. So this is I. And now we're adding zinc mercury with acid. So this is another reducing agent, just like tin and acid. So once again, alcohol is fully reduced, but now instead of having the nitro group, we have a ketone which can be reduced to just CH2. So we can fully reduce this acyl group into an alkyl group. And this is actually a method how, through Fiedel-Crafts acylation, we can get a straight chain carbon. So we get one isomer that looks like this, and the other isomer, the ortho is the ortho, so we get also the para isomer that loses that ketone to look like this. Now in J, what are we doing in J? In J, we're taking the product of D, then we're adding hydrazine and alcohol. So when we add hydrazine and alcohol, this is actually another way to fully reduce your acyl group. So this is actually a very specialized way of reducing your acyl group. So you actually will get the same products as in I here. So these reagents, so hydrazine and a hydroxide anion with zinc, mercury, and an acid, strong acid. These two reagents, although they're different, they're both reducing agents, and specifically, they will reduce your carbonyl groups or your ketones to straight chain alkene. So both I and J will give you the same products. So now what about in K? And this hydrazine and the mechanism for this is also shown in the textbook just for reference. But this is one of the cases where it's good to have a little bit of memorization in organic chemistry just to be able to identify these things quickly so you don't waste your time on a test. So J, we're taking the product in C. So let's take that product in C. This K. Whoops. We have two isomers. And we're adding bromine and light. So HN0 is light. So this is a radical bromination mechanism, and specifically, this type of radical-derived bromination occurs at the benzylic carbon. So your benzylic carbon is the first carbon off your benzene ring. So these are your benzylic carbons. So you're going to add your bromine halide onto these positions. So you'll have, once again, your two isomers. One adding the bromine off the ortho position, and one adding the bromine off the para position, benzylic carbon. And now, last but definitely not least, L. So L, we're also taking the product of C, and then we're using KMNO4 to fully reduce that. Or sorry, fully oxidize that, sorry. So we're also taking the product of C, and we're using KMNO4 to fully oxidize this. So what we know about KMNO4 is that it won't touch this alcohol, because if you were to put a double bond here, then this carbon here would get 5 bonds, and we know that's not possible. So only carbons that it can touch is this ethyl group that we added here. But some people might say that, well, we would have a carbon spacer and then oxidize this terminal carbon, but they would think that we would oxidize this terminal carbon, but KMNO4 is so strong that it's going to oxidize the first carbon off of benzene. So it's going to happen in multiple steps. First, we'll oxidize this into a ketone, then to an aldehyde, and then to a carboxylic acid. But the overall product is going to be that carboxylic acid product with only one carbon attached to it. So what I mean by that is that you'll have this carbon here being remained, staying on. Then you'll oxidize it with a double bond oxygen, but then we're going to have your carboxylic acid. So this carbon here falls off in a process of this oxidation, because first we go to a ketone, then aldehyde, then carboxylic acid. But KMNO4, you cannot isolate the aldehyde or ketone product. It's going to oxidize fully right away, instantly, to your fully oxidized carboxylic acid form. And you're going to have this with both of these isomers. And that's it for this problem.